In this short session, I will try to cover how AI has evolved across till today, and add just a little bit of foundation on what AI means. For starters, this presentation will not be very overly technical, or trying to be accessible as possible. So if you look at how AI has evolved, and currently how AI has taken up the public conscience and public conversations, it's important to look at how history has panned out for AI systems. So mostly, if you look at you can go back to 1970s, where early expert systems were being explored, and in 90s and 2000s, a lot of diagnostics and image interpretation algorithms were being explored. And now 2014 onwards, you see a lot of transition to modern AI algorithms that you see right now. So early pioneers in 1970s were mostly looking at rule-based AI systems, those that were called expert systems. But then again, you realize that rule-based systems are very fragile. It doesn't take into account the uncertainties. And so next generation of systems try to look at, well, can we do probabilistic reasoning on these kind of systems? And one of the milestone of this was IBM Watson winning Jeopardy and winning against humans in 2007. And so this showed that algorithms that process natural languages have come up really well. And now, as you see, there are more than hundreds of different FDA-approved AI-powered devices available and being tested in clinical settings, and more being approved, as you see. So this is where you are looking at in the milestone, right? So early expert systems, if you look at it, they were mostly rule-based, and the limitation here is they're hard to scale. I mean, for each diseases, you have to write your own rules. The rules may change. When you change the protocol, you may have newer understanding, so there's no new learning from new data. So, and also, these early systems were not really integrated into the clinical workflow. And so, and in 1990s and 2000 onwards, a lot of radiology image interpretation algorithms were being explored. For example, pioneering work in breast cancer detection from mammograms. Can AI do it? Can AI help us in screening for these mammograms at large national scale? And the problem was always, well, these are very promising algorithms, but still not yet deployment ready in clinical settings. And so 2000 onwards, there's a lot of still research being done. And now you transition to modern AI algorithms 2014 onwards, and you see a lot of integration of electronic health records. So a lot of digitization. This means a lot of data is being generated, data is being collected. And in addition to data, also a large amount of annotated data sets and hardware also being matured. So GPUs became so powerful that you could work on thousands of CT scans and MRIs and do segmentations and those sort of things. And so this has enabled breakthrough in medical imaging, generating clinical notes, drafts, and predictive analytics in hospital settings. Right. And so with this historical evolution and where we are right now, I mean, it's useful to understand what AI does, what are its foundation, how is it being built, what are its limitations, should we know any better? And so in this set of slides, I'll try to say what AI is and what AI is not. It's not going to be a complete introduction, but just for starters. And so some of the components of AI, mostly data, algorithms, and models. And also try to typify these AI algorithms that are able to predict, analyze, and generate. So when people talk about artificial intelligence, I mean, it seems like a very, it's an umbrella term, actually. So what AI does is, these are a set of computational systems that are designed to perform tasks that normally require human cognitive function, right? So human cognitive function, you cannot pigeonhole into one particular thing. And so these are not, AI is not one single algorithm, it's a spectrum of methods. And so if you look at medical imaging, you might look at algorithms that are able to perceive, that are able to detect patterns For example, on your left-hand side, you see an AI algorithm reading a chest X-ray and being able to tell, well, I can see a cardiomegaly at this certain region, right? So it's a perception part. And there are AI algorithms that are able to do language processing that can generate reports out of at least a draft report out of the chest X-rays, right? And similarly, being able to forecast, being able to understand diseases, find new risk groups and biomarkers. So roughly trying to categorize a single algorithm into spectrum of these 4 different components. And so if this is what AI is, being able to build systems that replicate human computer vision, human vision at least, so what AI is not? Well, for starters, AI is not new. Right? So since 1950s, people have been exploring it. And what counted as AI in 1967, so we usually mostly shifted goalposts, actually. So what counted as AI in 1960s, 70s is no longer what we call AI in the recent years, right? And in some ways, you can actually see AI algorithms actually being used. For example, if you look at clinical guidelines, these are actually simple machine learning algorithms, usually often decision trees or similar rule-based systems, and they look like they are represented in forms of clinical guidelines used for bedside triage rules, but underlying they are just linear probabilistic models, which are a fundamental basic form of AI in some sense, at least machine learning. So if you look at pneumonia severity index, you get some of the predictors, and it helps you identify low-risk patient with community-acquired pneumonia, for example. And so these algorithms, these basic algorithms are mostly transparent, interpretable, but I think the point of departure is now that the modern AI systems are much more complex, hard black box models, and so hard to be interpretable, and hard to audit and align with clinical reasoning, but again, research being explored on that front. And another additional example of that AI is not, that in some ways they are actually being used, but they are not explicitly defined as an AI. For example, in a pathology lab, you might have an automated hematology analyzers that look at cells and try to count. So manual cell counting is very tedious, time-consuming, can be unreliable, and so a lot of these systems come with automated cell counting systems, which are increasingly being replaced by modern deep learning systems, right? So you are actually using AI in your clinical setting, but it may not look like explicitly that you're using it, right? Even modern ultrasound systems and CT scan systems come with some form of AI systems built in, right? For example, fetal head circumference. So a lot of these are happening in the background, but not necessarily defined as an AI per se. And another point of departure could also be that the name itself, artificial intelligence, but usually the term intelligence is largely a branding term, I'd say, because since it's able to recognize patterns, but not in the human sense that it lacks semantic and contextual understanding, and so AI is not intelligence, right? It's pattern recognition, but a much more complex pattern recognition system. And so we've looked at what AI is and what AI is not. What makes a modern AI system? So what does it look like? What does it take to build such a system? And so the 3 main components are data, algorithm, and models. And think of this as ingredients, recipe, and the meal. You want to build a model, you need algorithms and data. You want to build a meal, you need recipes and ingredients. So when you look at data, there could be a lot of different forms. Mostly you're looking at medical images, but also structured and clinical notes could also be that. And again, the idea is garbage in, garbage out. And algorithms. So these algorithms are the fundamental building blocks that try to identify pattern. Early systems, more simplistic systems looked at like distance trees and logistic regression were quite popular that you see in your clinical guidelines. But more modern deep learning systems are much more powerful and able to extract patterns from complex data like CT scans and MRIs and such. And the model is what you work with, that you interact with. And that's what you get out of these algorithms. And let's see how, a simplistic example of how you can build such an AI model if you need data, algorithm, and you have a model, right? Let's say you want to create an AI model that predicts a 10-year cardiovascular disease risk based on some kind of predictor. So you list your predictors, age, habits and try to generate a correlation with risk of developing cardiovascular diseases. So first thing, you collect data, right? You go on camps, you collect as much data as possible and track them over 10 years and see if they contracted any cardiovascular diseases or not. I'm not sure you are able to see the mouse pointer, but I hope this is clear. So now you have data. You pick an algorithm. So in this case, these are mostly predictor variables, independent variables. So you pick a algorithm that deals with it, mostly logistic regression, for example. And so this algorithm will return a model, right? So these are numbers that the models generated, and these models are able to find patterns in that they are able to correlate linearly these independent variables with the actual outcome, the 10-year cardiovascular risk. For example, for smoking, the number might be 0.65. It tells you that smokers have 91% higher odds of CVD than none. So this is a very simple example, but again, modern AI systems not only look at these indicator predictor variables, but actually images and pixels, which are much more complex, which are much more nonlinear, and it's hard to define a combination that results in, say, that gives you a diagnosis. But the overall idea is that you have data, model, and algorithm. Data, algorithms, and you get a model. And again, I think a lot of these algorithms also relate to these modern algorithms. For example, limited generalizability. We need algorithms to be explainable. We want it to be transparent, and a lot of these are works in progress. As I go forward, I will quickly, briefly give examples of 3 different types of AI systems that you might look at. Earlier, I defined these AI systems as AI systems that are able to predict, that are able to analyze, and that are able to generate, right? So predictive algorithms, they learn from historical data. You collect the input variables, also collect the output. For example, in this case, you collect images and also clinical notes, and then tell an AI algorithm, say neural network, to discover a complex pattern that is able to tell you if this X-ray has cardiomegaly or effusion or any other disease or not. So a lot of these AI models are so good that they, in a very confined research environment, they're able to do as well as the radiologists themselves, but again, trained on the radiologist data itself. So these are predictive algorithms that are able to forecast the outcomes. And another type of algorithm are analytical algorithms that where you do not know what to expect, but want to look at all these large amount of data set and try to find if there are any structure. For example, let's say you have a lot of data, but you want to see if there are any relationship or any biomarkers that help you relate that with a disease condition. For example, here is an AI model that looked at optical coherence tomography images. In this case, there were 16,000 OCT images collected, and they were looking at disease macular degeneration conditions. And they fit into this AI model, and it clustered these images into different clusters where an expert can now look at it and say, well, looks like macular degeneration is related with intraretinal fluid, right? And these set of clusters are thick visible coherent hypertransmission, and this was not known. This could be a potentially new biomarker that was not known earlier. So this helps you accelerate biomarker discovery with the use of massive amount of data. Otherwise, you wouldn't be able to look at all these 16,000 OCT images and have it in your mind and churn if the relationship between all these images. But AI models can do that for you. Also, generative models are becoming popular, where you give a prompt to an AI model, and it will generate an image with that specific disease condition for you. For example, I want an image with a cardiomegaly and bilateral effusion. Here you are, right? And a lot of these algorithms are so good that they fool experts in being able to tell if this is synthetic or not. In short, I think I'll close this presentation with the takeaway that There is a lot of AI capabilities being explored, and also there's hope with radiology, so with a lot of AI, with a lot of images being taken, and the radiology workload burden increasing every day, and the amount of time available to interpret these images. I think we have to be hopeful that these AI systems are able to help us be more efficient and improve ourselves. Thank you.